Today what we have here is section 14.2 in the book, Wave Properties. These little videos are made to help get you through the book and to see what's essential within it. You'll notice on here there are bolded things. It's not in the book. These are things that I have bolded that you can take a look at. It sort of emphasizes some of the important things. So let's go. Wave properties, main idea. Waves transfer energy without transferring matter. That is really important. As it says on the top of this next page, a wave is a disturbance that carries energy through matter or space without transferring matter. And that whatever the substance goes through, whatever the energy goes through, that's the medium. And so mechanical waves travel through a physical medium, such as water, air, or maybe a rope. There are two types of waves, a transverse wave and a longitudinal. Trans, that particular prefix, means across. So if you take a look over here at figure 6, and definitely use these figures, you'll notice that transverse wave, bam, look, it goes perpendicular to with the way the rope goes. It goes across. And then it comes up, and then bam, the wave is going to go and now move that way. That's your transverse wave. Longitudinal waves, they go the lengthways. They don't go parallel, they go according to the length. So take a look at this one. You go and you, boom, collapse the particular spring like that, release it, and bam, the wave goes the long waves. And you can see that's what they talk about there on the right-hand side. And also notice sound waves, those are longitudinal. The next page basically shows the crest and the trough, the top and the bottom of a wave, and that's going to be important to us. There are many wave properties besides crest and trough. One is amplitude. Amplitude basically is the energy of the wave, and so it's how big that particular crest and trough are. So if you take a look, you'll see it says on the right-hand side, you'll notice wave A, it is much farther up from that central line. That central line, by the way, is called the equilibrium. And so it's much higher on wave A than it is on B. So the amplitude of A is bigger than the amplitude of B. Also notice the wave goes up on A first and then down. It's the distance from that equilibrium, whether up or down, which is the amplitude, but it's always from that center line. The next thing, as we said earlier, a wave's amplitude is the wave's energy. Bigger the energy, bigger the amplitude is going to be. Wavelength, down below. And so what happens here, wavelength is going to be from crest to crest or trough to trough or any one spot on a wave to the same spot on the next wave. Take a look at figure 10. You see on the bottom there are two troughs, and they have that really funky little symbol. That's called lambda. It's a Greek letter, and that is telling us the wavelength. So any spot between two waves that's in the same, like trough to trough, crest to crest, or wherever it might be, that is your wavelength. Now, with that, waves also have a speed. So how fast does a wave travel? Take a look at the equation there. V equals d over t. Hey, we've seen that equation. Speed or velocity is distance over time. So it's the same exact thing here. Also notice down below, speed depends only on the medium through which the waves move. That's incredibly important for us. Then what we get into is a particular thing, which is the period and frequency. And then down below, calculating frequency. Well, frequency is the number of waves, okay, that are going to be coming by per second. It's how frequently they come by. That's why it's called frequency. Now, unfortunately, we have a weird unit. It's called the Hertz, an HZ named after Hertz. And so what happens is that we've got to remember that it's waves per second, okay, that's going on. Now, frequency of a wave is also related to another thing called the period. Now, it would be nice if period was P, but it's actually T. But that's actually cool, and let me tell you why. Frequency, we said, is waves per second. Period is the reciprocal. That's why F equals 1 over T, and also T equals 1 over F. So what happens is that with the period, instead of being waves per second, period is seconds per wave, or time per wave. And so what occurs is time, T, big T, period. That's how it helps you. Also notice that there's a relationship between the wavelength, that lambda on the right-hand side, which equals V over F. We can also say that V, if we go and multiply the F through, V equals wavelength times frequency. We're going to be using that equation a whole bunch. Now, as you go on within this chapter, what you'll notice is at the very end, they have a section for self-check. And you can do these. So for instance, a transverse wave travels what to the direction of the wave's motion? Well, if you recall, trans, across, perpendicular. So if you hit that and you can check your answer, woohoo, got it right. What does a wave carry? Energy, particles, water, light? Well, in this particular case, we know energy. We're correct. And you can go through and do the other ones to check how you're doing and how you're mastering what's going on. So get started on that launch homework. We'll talk about this stuff